So we start the second session of this conference, and we have lectures in this conference. The first one in this session, the first one is by Professor Kandalam Ramachari, Rowan University. Professor Kandalam Ramanujachari obtained his Masters in Chemistry from Andhra University and PhD in Chemistry from IIT Madras. He worked as a postdoctoral fellow in solid-state chemistry at Rutgers University.
I also would like to especially thank Vishal Shaini for inviting me to this conference. I was trying to see where I would fit into this. I'm not a computer fellow, but we make materials that make the computers run a little faster. Gone are those days, perhaps in very next few years, that we may not have separate processors and hard drives. One of my research projects is to design computers where you will have the processor and the hard drive in the very same material, which is by designing novel dilute magnetic semiconducting compounds in nanoscale. Well, I'm not going to talk about those efforts, but what I primarily intend to do today is to, for the students who are sitting in the back, tell them a little bit about what the magnetism is, and for all of us, we need to also review some of the opportunities the nanomagnetic materials present, and also some of the challenges that they give us. How we can perhaps utilize these materials in designing for novel applications. So that will be my emphasis of the talk today. So let's give you some idea about my outline. I will also talk about nanotechnology and what is nanotechnology and why is it important now. So that's one area that we will touch upon later on. We'll also talk about some fundamentals of magnetism, exactly how do these materials turn out to be magnetic, what makes some of them ferromagnetic and what makes some of them antiferromagnetic, some of them metamagnetic, some of them spin clusters, all kinds of frustrated systems also one can see. As you all know, magnetism is the oldest science known to humans. Long time ago, people used to use these magnets to navigate themselves in the seas. But that is, I would say, unfortunately, that's the least understood science to even today. With so many years of acquaintance with magnetism, we still don't have a comprehensive handle. So I'll try to get to those aspects as well. I'll also talk about some of the applications of the magnetic nanoparticles in a variety of industries and technologies too. And after that, we'll have a slide on conclusions. So, for those of you who are sitting in the back, the students especially, I'm sure most of you have taken 1 or 2 semesters of chemistry. You all know that the atoms have electrons, and some are paired, some are unpaired, and especially if an electron has a charge, and if it moves, it is supposed to produce magnetic field. That's what the classical physics tells us. So if I have a lot of unpaired electrons, then you will have collectively a large magnetic field within the samples. Now that is where we're going to hit at. Now, the magnetic moment itself, the origin of it, comes from the electrons within the atoms of the solid. So now, as a chemist, what we try to do is design the solids in a way that place the atoms next to each other so that the magnetic moments of the one atom correlates with the next atom and try to give us some novel properties. There is no theory, unfortunately, that will predict, well, if you design this way, this is going to be ferromagnetic or antiferromagnetic. I think the best thing you can do is make it and do the measurements, and then the theory comes later on. But so that's the overall magnetic moment. If I can see the slide here. So that is where the Bohr magnetons, which is given by the EH over 4 pi me, where mass of the electron, this is your Planck's constant, and the total spin moment is given there. For those of you who have taken 1 or 2 semesters of chemistry also know that not only electrons spin, they also orbit around the nucleus. So there are 2 types of magnetic moments that way. Because of the spinning, you will have a type of magnetic moment. Because of the orbital motion, you also have a magnetic moment, and sometimes this can present a problem because they can get coupled or they can get uncoupled. In some cases, the orbital moment cancels itself. You will get only spin-only type of moment. So we'll try to see those cases. If you look at titanium 3+, which is a D1 configuration, that means there's only 1 unpaired electron in this. The total spin quantum number is 1/2 because there's only 1 unpaired electron. And if you calculate the magnetic moment using the equations that I showed you in the previous slide, that comes to around 1.73, assuming only spin-only contributions. But if you also assume the orbital contributions plus the spin contributions, the total comes to about 3.01. But experimentally, always titanium 3 plus gives magnetic moments in the range of 1.7 to 1.8. So what does that tell us? Does the orbital moment contribute to the magnetism or no? No. So clearly I see one head saying no. Yes, in the case of titanium, the magnetism is purely the spin contribution only. There is not much of magnetic contribution from the orbits. If you go to vanadium 3 plus, that's a D2, the total spin is 1, 2.83, and again if you look at this, you seem to have sometimes a very small orbital contribution to vanadium. When you go to the chromium, again the case is very clear, and same thing with iron, nickel, and copper. I did not put the cobalt here, but the cobalt does have a very strong spin orbit couplings in the experimental values. Now, anytime you have an orbital contribution, you will have magnetic moment slightly off because you are not taking into consideration the orbital moment. And also the spin orbit coupling increases the moment of the ions with these configurations, D6, D7, D8, D9, D9 being the classical copper 2 plus and D8 being classical nickel 2 plus ions, and decreases the moment of the D1, D2, D3, and D4. This is how the LS coupling is arranged. For the less than half filled shells, this is L minus S, and more than half filled shells, it is going to be L plus S. All right, so the magnetic ordering. So if I have a collection of atoms with unpaired electrons, you can have several scenarios. I'm not exhausting all the possibilities, but I'm giving you here a random orientation of the spins on the neighboring atoms. If that happens, the material is said to be paramagnetic. And if I have moment on the one atom pointing up and pointing down on the next atom, and if the lattice is arranged this way, as you can see very well, the net moment is going to be 0 because you cancel the magnetic moments of the neighboring atoms. So such cases we say the material is antiferromagnetically ordered. On the other hand, if all the moments are aligned in the same way, we call this ferromagnetic material. In some cases, in some complex solids, you may have uncompensated spins. Like for example, you may have a preferred orientation this way, but the moment on the other side is not completely cancelled. So in such cases, we call those ferrimagnetic materials. So these are 4 important classes of magnetic materials. In general, at very high temperatures, most materials are paramagnetic. When you start cooling them, they may turn antiferromagnetic or ferromagnetic or sometimes ferrimagnetic. So most of the time, experiments only will tell us. Regardless of whether they turn antiferromagnetic or ferromagnetic, at the high temperature region, most of the time, the magnetic susceptibility, which is defined as the magnetization to the applied field ratio, is given by an equation C, which is the Curie constant divided by the temperature of the system plus a Weiss constant, which kind of tells us whether the system is going to order antiferromagnetically or ferromagnetically. So by measuring the magnetic susceptibility as a function of temperature, which I will show you the plots in the next few graphs, one can estimate the Curie constant, which will tell us how many unpaired electrons an atom has. That is how you can retroactively find out whether my oxidation state of the metal is 3 plus or 2 plus or 1 plus, because transition metals, as you all know very well, can exist in multiple valence states, and this is one way of figuring out this. So I'll show you now a couple of plots here. So on the left here, you're looking at the molar magnetic susceptibility of an iron 3 plus compound as a function of the temperature. And this iron 3 plus, if it is a free ion, then it will show a classical paramagnetic behavior. As you cool down the temperature, the susceptibility raises with a theta equals 0. That theta 0 implies that there is no net interaction between the iron 3 plus atoms. On the other hand, if the interaction is antiferromagnetic, you will see a plot like this, and if it is ferromagnetic, you will see a plot like this. Again, it's the same iron 3 plus. Depending on the network that is placed in, you will have different type of magnetic properties. So this is a very exciting way of changing the magnetic properties of the solids. So if you take the same data here, plot 1 over chi, which is the inverse molar magnetic susceptibility as a function of temperature, you can see lines. If it is a paramagnetic substance, it will cut the 0 because there is no theta contribution here. But if it's antiferro or ferro, it's going to cut the x or y axis in the negative sides. So this is the details of the magnetic calculation. So this is how you figure out from the experimental values how many unpaired electrons the system has. So if it is 0, it is paramagnetic, the spins are independent of each other. In other words, there is absolutely no interactions between these two atoms. They are not communicating at all. On the other hand, if they communicate in a positive way, that the spins are aligned in the one direction, we call that ferromagnetic, and if it is negatively aligned, it is anti-ferromagnetic. So if a material really turns ferromagnetic, this is how you will see it in the magnetic susceptibility versus temperature plot. So as you cool it down until a certain temperature, the susceptibility increases very slightly, but below a critical temperature called the Curie temperature, the susceptibility shoots up. So when you see a signature like this in the magnetic plots, you know the material is ordering ferromagnetically. On the other hand, if the susceptibility increases to a critical point and then drops, that tells you perhaps the material is ordering anti-ferromagnetically. Of course, you have to do much more studies before you can put these names that the material is ferromagnetic. I will not have much time to give an extensive lecture on the magnetism, but I'm just reviewing some of the fundamental things here. So the Curie-wise law is basically pure paramagnetic is typically only above, valid is only when the temperature of the measurement is 3 times the Tc. So if your ordering is 100 Kelvin, the sample is truly paramagnetic only about 300 Kelvin. So that is the general rule of thumb that we use in our studies. Okay, now the question is, I still did not answer why some compounds show ferromagnetism and some show antiferromagnetism. Can we predict? Given the structure, if I know the crystal structure of the material, how the atoms are arranged, what is the angle between the atoms, and if I know the distance between the atoms, can I think of a qualitative model that will perhaps help me predict whether it is ferro or antiferro? That's what I'm going to talk about in the next couple of slides. So let us see. Let's get some chemistry done here. How many of you have done some chemistry, one or two semesters? I'm sure not the professors here. I'm talking about the students. Yeah, you all have done some of it, right? So let's see I'm talking about a compound in which I have a manganese 3+ ion, an oxide ion, and a manganese 3+ in a line. So that's the situation. You all can imagine. We have Mn3+, O2-, Mn3+. Now the oxygen has completely filled orbitals. So I have completely paired electrons. Manganese 3+ is a D4 ion. I'm putting it as a high spin case here. So there are 4 electrons, 3 in the low-lying T2G and 1 in the upper levels of the EG. So these are the same identical ones. Now the question is, how would these two manganese atoms communicate? Would they communicate with the spins up like this and up like that, or would they communicate anti-parallel spins? Let's look at the cases here. I'm now giving you a scenario where I'm putting the spins of the manganese 3+ here parallel to the spins of the manganese 3+ on the next one. Let us see if this is a happy situation or not. As you know, quantum mechanically, statistically, you can put one of the electrons into that side, and let us say if that electron goes this side. Is that a valid configuration? Is that valid here for this? I think it is okay, but how about this? Is that a stable configuration for manganese 3+? As you all know, the Hund's rule of maximum multiplicity tells you you cannot have that spin down there. You have to have all the spins up if you are occupying singly the orbitals, correct? So this is not a good scenario, so I would say that's not how the manganese spins are going to interact. So let's look at a different scenario. Now what I have done here is I put one of the manganese spins down and the other manganese spins up. So the net moment of this manganese is pointing this way, and the net moment of that manganese is pointing that way. So clearly we're talking about an antiferromagnetic type of relationship. Let's see if that works here. Again, I'm going to transfer one of the electrons from oxygen, and you see I'm not violating any of the Hund's rules here. So as a result, whenever you have two manganese 3+ ions next to each other, the ordering generally tends to be antiferromagnetic, not ferromagnetic. In fact, I have examined hundreds of manganese 3+ compounds. I'm yet to see any manganese 3, oxygen 2- manganese 3 showing any ferromagnetism. So typically, we all see only antiferromagnetism. Of course, one can apply these rules for different cases. You can sit down near a drawing board and look at different types of ions or play the same game and see what type of magnetic ordering you might be able to see. And most of the times, you are right. There are exceptions, of course. And in addition to the super exchange that I showed you before, we also have a different type of exchange called a double exchange mechanism. Here again, I'm looking at two manganese atoms. This time, my game is different here. I have manganese 3 plus, spins up, manganese 4 plus, which has one less electron with only 3 unpaired electrons. Now, I'm putting it up this way. I'm trying to see if I can have a double exchange where instead of transferring the electrons from oxygen to manganese, I'm trying to transfer the electrons from manganese to oxygen and then move. Let us see if I play this game. You see now, I have put my electrons from one of the manganese 3 plus to oxygen, and the oxygen electron goes outside. As you all know, this is okay, manganese 4 plus. How about this oxygen? The configuration, is that possible? 2 spins, yeah, 2 up spins in the same orbital. As you all know, the most fundamental chemistry tells us, no, this cannot happen, right? So this is not a very good situation. In other words, you cannot have manganese 3 plus spins going up that way and manganese 4 plus spins going that way. So you cannot have antiferromagnetism here. So let's see the different case here. Suppose if I align the spins parallel, manganese 3 plus and manganese 4 plus, okay? I also want you to follow this slide very carefully. When I'm playing electrons, I'm not playing a game here. I'm teaching perhaps 2 different things at the same time. I'm moving electrons, which means I'm inducing some kind of electrical conductivity in the material. At the same time, I'm also looking at the underlying magnetic lattice. So I'm now looking at 2 different things. So let's watch this. Okay, all right. So that electron goes there. And as you can see now, this is a good arrangement here. So what does it tell you? The spin alignment of manganese 3 plus and 4 plus, if I have 2 of them next to each other, that is supposed to be ferromagnetic material. In fact, the research in the last 10 years has been extensively on this work to see if I can somehow increase the transport properties by applying magnetic fields that led to the big area of magnetoresistive materials, which are also used in computers. In computing applications for data recording, retrieval, you need this technology. So you need materials that have superior magnetoresistive characteristics. And generally, compounds with manganese 3 plus and 4 plus have about nearly 100% efficiency compared to the cobalt nickel multilayers that are used today. Although there are some small problems technologically we need to overcome, but this is again a fundamental knowledge of chemistry that helps us design materials for advanced applications. And our group has published quite a lot of work on these things. In addition to the paramagnetism, antiferromagnetism, ferromagnetism, we also have different types of magnetic materials are called spin glasses. When I was listening to Professor Bennett's talk before, he was talking about the communication of electrons. Now here is a spin glass, which we call is a very chaotic system, where you have a metallic element, and then you have 2 magnetic centers spaced, all right? At some low temperature, for some reason, which we don't know why, these 2 atoms communicate with their spins. That fellow will say, my spin is up. The other guy will say, well, I'll also put my spin up. How this communication happens on hundreds of angstrom scales, which is very difficult to even predict, to model. So these are our spin glasses. We have examined at least 15 or 16 different systems with spin glasses, and we published the work. In addition to spin glasses, we have cluster glasses. We have materials that are antiferromagnetic at certain field. When you jack up the field a little bit high, the material turns ferromagnetic. Such materials are called metamagnetic materials. We have investigated them too in great detail, and we also have materials we call super paramagnetic materials. That means you have magnetic clusters in which within the cluster the interactions are ferromagnetic, but between the clusters they're all random, making it something like a paramagnetic material. All right, so I just will quickly review these things here. In general, what we have done so far is we have looked at diamagnetic materials, materials that have only paired electrons, no unpaired electrons. Talked about ferromagnetic, paramagnetic, antiferromagnetic, and ferrimagnetism. We also talked about a couple of mechanisms, models, that will help us predict the type of magnetic order the materials can have. And within the models, we looked at the super exchange and the double exchange. So now, coming to this conference theme, nanotechnology. Now the question is, why and why now? What exactly are we trying to achieve here? Feynman, in fact, Goswami's book also, he has, I think, read, I think, either you or Vishal Shaini, together, is that that book started with Feynman's, I read that book, that was wonderful that you have chose to quote his words. So I'm adding a few other things, what Feynman has said, to what you already have written in that book. Let us say that there are about 24 million volumes of interest in the world, and I have assumed that each of my 24 million books is as big as an encyclopedia, and I have calculated then how many bits of information there are, approximately 1,000 terabytes, about 10 to the 15 terabytes of information. Now, if you could store at least one bit of information in 100 atoms, I'm being very generous here, you can put 100 atoms for one bit of information, even assuming that you can have all the information pretty much stored in 1/200th of an inch wide, which is barely a piece of dust you can't even see with your own eye. So that is the amount of information you could store in such a small space if you have the patience, perseverance, knowledge to design such materials. That is where our group is after, to make materials small enough that with functionality where we can store a lot of information. So Feynman in 1959 predicted that there is plenty of space in the bottom. That's a very famous saying, almost everybody uses that thing. So why nano? One of the very important things that we have realized that materials at the nanoscale behave remarkably different compared to the same composition in the bulk. As soon as you reduce the dimension of the material, suddenly we see the emergence of novel properties, and that's one of the reasons why we study the materials at the nanoscale. So that is the left is your bulk. As you see, very few surface atoms compared to the bulk atoms. As you reduce the dimension of this material, you have now relatively more surface atoms compared to the bulk atoms, and that kind of changes a lot of parameters. As you all know, gold, which is yellow in color, in the nanoscale, it glitters not yellow, but like red. I don't know if you have seen nanoparticles of gold, they exhibit red color. So it tells you, it changes your optical band gaps. And what else it can change? It changes the melting point. For a long time, classical chemists and physicists were thinking that the melting point is an intensive property of a material. But now we find you can play with the melting point of the material by changing the dimensions. Very recently, we have published some work on that area, that by reducing the dimensionality, we were able to show the DSC, DTA, the melting behavior of the materials, and there is no question about it. And also the magnetization. What is a ferromagnetic material in bulk may not be ferromagnetic when it is nano. And the ability to hold charge, the supercapacitor effects, and the structure, the entire bulk structure, if you try to go to the nanoscale, that we find appearance of very different type of structure. Chemical reactivity is very different for the nanoscale compared to the other thing. In a way, there is a day and night difference between the bulk and the nanoparticles, and that's what excites us to see, to make the bulk materials and also the nanoform and compare and contrast the properties to see what we see and what we don't see. I'll give you some examples as well. So Bill Clinton, some time ago, before the America got hit by the 9/11 unfortunate episode, had some ideas about what we should be doing for the next 10, 15 years. So he wanted to have a device that's the size of a sugar cube that generally basically holds all the information of the US Congress, which is volumes, tons and tons of volumes of books, and making materials and products from the bottom up, not top down. A lot of nanochemists take the material and try to chop it up to make it nano. That's what we call top-down approach. In top-down, there's a lot of wastage. So we try to make materials from the bottom up, which is a more efficient and greener way of doing the nanochemistry. And developing materials that are 10 times stronger than steel but a fraction of the weight. These are all the White House directives from the President's office. improving the computer speed and efficiency, memory chips by factors of millions, detecting the cancerous tumors that are only few cells in size using nano-engineered contrast agents. I'll talk a little bit about this because some of my work that is going on in my group is in that direction of detecting cancer cells early on, and removing the finest contaminants in the water, purification of the water using the nanoparticles. These were some of the goals. Not only the goals, they also have the money to support this. For example, NSF has committed about $305 million, and Department of Defense, Department of Energy, Health and Human Services, Department of Commerce, NASA, Environmental Protection Agency, Department of Homeland Security, Department of Justice, all these people are putting money to support this effort, and my projection is our technology may reach about $4 billion in 2009, and the commercial market is approximately 10 to 100 times as big as the R&D market. So there's a lot of interest in this one. So in view of the time, I think I would like to skip this part of it because I don't want to eat the time off. So just bear with me quickly. I will just go. Although this is a beautiful work, but we'll get into the part of the nanomagnetism. So magnetism at the nanoscale. So what are the things that you can do? If you look at the grand challenges in nanomagnetism, ultra-strong permanent magnets with a very high coercive field and very high remnant magnetization. Unfortunately, today's magnets, if I have very high coercive field, we have very low remnant magnetization, and vice versa. If we want to have both, we just don't have a material. But recently, some of the designs, what I see in the literature, by combining the nano and the bulk, you can engineer the materials to have very high coercive field and very high remnant magnetization. So that's a possibility. Ultra high density media, that's always information hungry people. Spin transfer with gain, spin polarized materials, room temperature magnetic semiconductors. This is my dream too. Like room temperature superconductors, if you can have a magnetic semiconductor at room temperature, you can retire for your life because that's how hot these materials are. Instant boot up computers, you can use nanomaterials, magnetic logic, spin-based qubits. There are so many nano biomagnetic sensors. So this area is very large. That is why the research in this nanomagnetic materials is very attractive. I'm giving you some examples which we have done in my lab. If you look at the nickel oxalate dihydrate, which is NiC2O4, 2H2O molecules, when you look at the magnetization as a function of temperature, as you can see, this is reminiscent of the antiferromagnetic transition. And when the bulk material shows 50 Kelvin transition, the nanoparticles show approximately 45. So in other words, there's a reduction in the anneal temperature when you cut down the size. Here is a cobalt oxalate dihydrate. When you look at the bulk material, it has the 18 Kelvin antiferromagnetic transition, but when you make it nano, you see an enhancement in the Tn. So in one case, the Tn goes down as you bring the size down. In the other case, the size, as you bring the size down, the anneal temperature goes up. That's kind of very fascinating. How many materials can you do this? I mean, you're not designing new materials. You're taking the same material, breaking it down, and then changing the magnetic transition temperature. How cool it is. If you really think about it, this is really beautiful. So same thing that we have done for the copper. We have done 25 nanometer particles, 80 nanometer particles. We looked at the magnetic transition. You see, if you have 25 nanometers, you have 80 Kelvin transition. And if you have 80 nanometer particle, the temperature is about 220. So you see the magnetic ordering temperature changes. So you can tailor these things. So by reducing the size, I have a feeling if I can make a 2 nanometer particle, I can completely wipe out this transition. Although we were not able to make that particle, but that's our thing. So you can tailor the magnetic properties. Similarly, cobalt 304, which is a very important material in solid state chemistry. Here also, you can play with the size effects, and you can see very interesting development of magnetic properties. So why is industry after magnets? As you can see here, even if you look at just the automobile industry, how many places the magnets are used? I'm not going to wait till all of you read this, but trust me, there are a lot of areas where automobile industry needs magnets. So if you want to go for nano cars, I don't need to tell you that we need to have nanomagnets. So to do these things, what we do is we encapsulate some of the spins into a small particle by using reverse Meissel techniques, and you can combine the overall magnetization to give you a super spin moments, and we can look at the exchange anisotropies and finally find out the radius of the, not the nanoparticle, but the effective magnetic field. So you can tailor these things too by choice of proper materials. Like for example, if you have iron, that radius is about 6 nanometers. If you have very strong SMCO5 permanent magnets, that radius is 764 nanometers. That is not the radius of the particles, it is the radius of the superparamagnetics domains. By changing the radius of the particles, you can also change the coercivity of the magnetic fields. So that graph was worked out about 10 years ago, where you can change the particle size. With that, the coercivity also changes. So the other aspect, of course, it's completely evolving right now, is the life sciences. As you all know, iron is very vital to the living things, both for the synthesis of the hemoglobin, and some of the animals at least use the magnetic fields to navigate themselves. And there are enormous number of medical applications that are listed here that might benefit from the development of new nanomagnetic particles. So just to give you a perspective of where we are, that is a slide that I borrowed from a colleague from the biology department, where it gives you a perspective of where we are in terms of the sizes. So that's the smallest one, the aspirin molecule. That's your size of the DNAs, proteins, viruses, bacteria, and other cells. They're all the relative time scales. As you can see, this is where the nano regime can be very important in terms of making materials, drugs that can hold to proteins and the DNAs. The magnetic imaging, magnetic heating, targeted drug delivery, these are all very important things that are coming up right now. And magnetic sorting, for example, you can take a magnetic nanoparticle right here, you functionalize it with a group, and you can take these functionalized magnetic nanoparticles, put it into cells that have different types of things, and these nanoparticles selectively pick up those cells that have that functional group compatibilities. So once they cling onto it, you can apply those things and apply a magnet, for example, and separate them out. So this is a beautiful way of separating cells. If you have a mixture of cells, and if you want to target some of the cells, you can use the magnetic nanoparticles, hold them, and then use a magnet to get them back. It's a very simple magnet principle. Hyperthermia is another thing that is picking up a lot of interest in the magnetic nanoparticles. As you all know, most of the tumor cells die about 42 to 46 degrees Celsius. So by injecting magnetic nanoparticles in the affected area, the magnetic nanoparticles generate a lot of heat because of hysteresis, Brownian motion, and eddy currents. So that temperature increase in the local area will be enough to kill the cancer cells. So that's again a big important development that's going on. The human clinical trials are right now, they are being done right now in Germany. Although I think we are in India, I think we are way behind because we don't appreciate all this. But these are the true things. This is a very important area of science, and we should put our things. And magnetically targeted drug delivery. Drug delivery itself is a very challenging task. As you know, most of the small kids and the older people, it's very difficult to give drugs to them, and they don't take it in time. So if you can load a magnetic nanoparticle and with the drug, and if you can inject it inside, and if you can have time release, controlled time release, that will be a fascinating application, which is also being done. As you can see here, there is a lot of studies, time release, delivery of the multiple drugs, biodistribution. These are all the studies that are being currently done on the magnetic nanoparticles. This cartoon basically summarizes, like if I have a mouse that has an affected area, that's a tumor there, what we do is we take a syringe, put in the magnetic nanoparticles that are functionalized, and use an external magnet to guide it exactly to go to the same area, rather than going all over the place. And then those particles, they can deliver the drug and perhaps kill the cancer cells. Right now, as you all know, the therapy that we use is not practical because we kind of kill a lot of normal cells too. And that's why a lot of cancer, people who are on cancer, anti-cancer drugs look very sick because of this problem. So that is one thing that magnetic nanoparticles can do this. So of course there are some issues with the magnetic nanoparticles. the drug loading capacity, because the particle size is very small, the amount of drug that you can hold onto it is very small. There are, of course, some challenges on the aqueous dispersion stabilities, circulation time, and biocompatibility, and retention. And of course, the last one is, how do you get rid of the magnetic nanoparticles after they're injected inside? How do you bring them back? That's a big challenge right now. So there's some interest on organic magnetic nanoparticles that may be biocompatible. So they will do the job and die away inside, so you don't have to bring them back. So I'm going to skip this part too, because of the lack of time, because I want to give the speaker the 3 o'clock time I was told. Let us come back to some of the applications of the nanotechnology, some of the benefits and the concerns. Everywhere in the world, there is a concerted effort now to make the nanomaterials. But one thing that we have to be very careful about, I tell all my students, is nanoparticles are extremely deadly. They're so small, they can penetrate the human, because our skin pores are much bigger compared to the particles that you're making. So no mask can really stop you. So you've got to be extremely careful. And there are a lot of people who are dying. Some of the students, especially those in the back rows, got to be very careful if you are working with the nano. But here is the question somebody asked: if there is a technology that is going to change the world but will kill 50,000 people a year, would you go in favor of it? It's a simple question I'm asking. It's a great technology, but it's going to kill 50,000 people every year. Would you go for it? Can you spend 50,000 people? Can you? No? No? What is that doing? Isn't it true that a lot of people die in car accidents every year? More than 50,000 people. More than 50,000 people, but still we use it, right? So what's the mantra here? That you got to be very careful and you got to follow some rules so that you don't get killed. So, in fact, these are all the official studies that in 2003, 2004, 2005, they have found that the nanoparticles definitely have a lot of bad effects and extensive damage to various parts of the human organs. So one has to be very careful. So, in conclusion, I would like to tell you a little bit about the nanotechnology, where it is used. You may not even realize it is being used. It increases the chewiness of the chocolate. So Chocola gums, sugar-free ones, use nanoparticles, nanocrystals, to increase the texture of this. And this is your L'Oreal skin creams. As you can see, this is your active ingredient, and that's your biodegradable shell. These are called core shell nanostructures. And when you make these things and deliver it to the skin, unlike the big ones, the nanoparticles can deeply penetrate inside and cure the skin defects. And that is your L'Oreal cream. You can buy it. That price of that is $12.95. That has the nanoparticles or core shell nanostructures. And Buckyballs. These are all the Fullerene C60 face cream. You can buy that small jar for $250. They say that that has some kind of a reverse aging effect. I don't believe that, but there are some people who are willing to put that money because anytime they see a nano, they are so fascinated by that. But they do have some antioxidant properties. Baseballs, they are going for very high prices. They are very light and they give a very good kick factor. So these are again done with magnetic, non-magnetic fibrous nano materials here. Stained fruit fabric is again a very fascinating thing. If you can put some nano materials inside, you can design your clothes so that nothing sticks to it. So this is again the magic of the nano right there. And socks, for example, if you can put small silver particles, extremely 10 to 15 nanometers, silver particles in the socks, basically you will get rid of all the smelling problems sometimes people have with the socks. And it's a permanent resistance to odor and fungus. So there are a lot of benefits for these things. And there are some windows now that if you put a nano coating, They have self-cleaning abilities. That is, again, it's available at certain home improvement stores. There are other possible advances, wear-resistant tires that are being now tested, environmentally friendly dyes and pigments for the nanometer scales, especially they are very good in trapping pollutants, and computers with the capabilities of the current workstations the size of a grain of sand, because that's the kind of thing that will believe that the nanotechnology is going to revolutionize. And the spacecraft technology. Today the spacecraft is so heavy, but by putting nanotechnology we can reduce the weight of it, so we can use less fuel to explore the outer space. So basically, I'm sorry, I just had to rush a little bit in the middle because I wanted to give the floor to the next speaker by time. I think I tried to do, impress upon you the importance of the nanotechnology, some of the magnetic nanoparticles, and where we are in that game, and where one has to be very careful in terms of the synthesis and the applications of the materials. So clearly, a lot needs to be done, and that is why, if you are wondering why the government of India is putting crores and crores into nanotechnologies, I'm just trying to give you a justification. These are all the areas that will affect us: the health, the life sciences, the technology, the computers, the automobiles. I mean, name any technology that we use, even the cell phones. The nano is going to definitely revolutionize, and it will economize. You don't have to use a lot of material compared to the bulk technologies. So with that, I'm sorry I took 5 minutes more. I wanted to finish by 3, and thank you, Dr. Goswami, and thank you all for your attention.